Welcome to a very short talk here. Really no need to take notes here. I just want to put together, bind together, if you will permit me the pun, a few ideas in science that normally don't get put together. I mean, they were never put together for me. But I think it's a big unifying principle, and I kind of wanted to, back out to 10,000 feet and look at this issue of potential energy and bonds and binding energy and stuff like that. So this, kind of glib description of potential energy is like stored energy in the system. People are always translating potential energy to be some kind of positive energy. And of course, you're free to do that because you're free to set the 0 point. But really, there is only one proper way to set the 0 point, and that is if the two objects are no longer interacting, right? So if you take a rock so far from the Earth that it doesn't feel its gravitational force at all, then you could say there's zero potential energy between them, right? Same thing with like two negative charges or two positive charges. And so once you have this idea of freedom being or no interactivity being the 0 point of energy, then the positive and negative signs get set for you. And they make sense, and they put together a lot of other things. And I wish textbooks would be more explicit about this and sort of agree on this convention. But let me walk you through it, right? So you have positive energy if the objects actually are repelling. So in that sense, there is some stored energy. The objects are not bound to each other. For instance, two positive charges, if you force them very close together, they electrically repel, and that electrical potential energy between them is released and comes out as kinetic energy if you let them go, right? So anytime you have two objects that are interacting but they're not attracting each other, then sure, yeah, I would agree that that's a positive potential energy, and you can extract it from the system readily, right? But all gravitational interactions are actually attractive. And so therefore, when you release the rock and it falls towards the Earth, what I want to walk you through and try to convince you of is that is not a case of positive gravitational potential energy becoming freed, right? Instead, the rock is actually becoming more bound to the Earth as it falls more closely to it. And it's down here in this negative energy regime, right? So positive charges attract to the negative charges, nucleons in the nucleus that are attracted by the strong nuclear force, and all gravitational interactions. It's my claim to you that those should be rightfully thought of as all negative potential energy situations. And here's the idea, right? Is if when we say things are bonded together, that means there's an attractive force that is holding them together, and that means that they require energy from the outside world in order to break those bonds, right? Chemistry teachers are always harping on this, right? It always takes energy to break the bonds. Even if you have an exothermic reaction, the work to break the bonds between the reactant elements is required, right? You have to put energy in, and then it's only when the new bonds are formed amongst the products, if those are stronger bonds, then there is more energy released than you took to break them, and then the entire reaction is exothermic, right? I mean, generally we learn this in chemistry and then we forget about it and we go back to sort of naively thinking about, like, I don't know, some kind of stupid model where we see these bonds breaking and energy coming out of it, right? Which is totally not the case, right? Like I said, any attractive bonds you should think of as having negative energy, and that negative energy means something. That's the amount of work you'd have to do to free those two objects, right? So in all of these cases, when energy is being released between attractive things, you have this picture on the right here that I would like you to think about. You're going from a weaker bond to a stronger bond, and it's always negative energy, and the energy released is the difference between the shallow weak bond and the deep strong bond, right? And of course, in a lot of textbooks, they'll take this zero potential energy line and they'll shift it to the bottom of this chart, and just to make all the numbers even, they'll even bend over backwards to make numbers that should be negative positive. But whenever people talk about the energy in bonds, attractive bonds, they should always use negative numbers. So let me just walk you through three examples, right, from each of these three domains. right? So the first one is the lie that we tell in physics frequently, right? We even give you this formula. I did too, right? I'm guilty of it like everyone else. Say, oh, let's use simplified gravity, and we'll talk about the potential energy mgh. You get this nice positive number that's bigger the higher you lift the rock above the surface of the Earth, and you get all that energy released as it falls to the ground. And when it hits the ground, I'm going to call that h equals 0, and it has no more potential energy, right? But that's all just a gross simplification, right? We know that mg is not even the true gravitational formula. So let's look at the reality, right? So here is the actual gravitational potential energy that you can see should remind you of universal gravitational potential energy. G m1 m2 over r squared would be the force, and so this is the potential energy function. Notice that it does come with a negative sign in here. It formally is negative. And so this actually follows what I was talking about on the previous chart, right? So when you lift up, this is the surface of the planet right here, is the deepest you can fall into the well. The most tightly bound the rock will be is when it's on the surface of the planet. Then as you lift it, you're trying to free it from the Earth's gravity, right? So you're headed towards 0 as you get farther and farther away. So this little, mgh that falls from here down to here, we do two things. We set the 0 point to be down here, and we pretend like these are positive numbers, and we make a linear function out of this, when of course it is a curve, and it is all negative values, right? Now, the advantage of thinking about it this way, even though it's more complicated, is it's a better reflection of reality, right? The rock, when I lift it above my head, is still bound to the Earth. It still would require more energy put into the system in order to free it, right? And when it falls towards the Earth, yeah, it releases energy, but where does that energy come from? It comes from being a small negative number to a bigger negative number, right? So that is a loss of potential energy, right? If you go from like -7 to -10, right, that's a delta E of -3 joules. And so that reduction in gravitational potential energy comes out as kinetic energy, and the rock is moving faster, right? So everything still works out. But the advantage of thinking about it this way is you're acknowledging the bound system, the nature of the rock-Earth relationship. So a little bit of a lie that physics teachers tell you to simplify the situation. So let's go back a year and talk about chemistry class and the lie that most chemistry teachers will tell you. And this one usually is about the mass of the different nucleons, right? And they'll talk about the binding energy, and they'll talk about a mass deficit, and they've got all these complicated things, and they'll usually show this chart here with positive numbers. And so the energy per nucleon usually is maxing out here at element number, I think iron is element number 26. Looking over here at the periodic table. Yeah, I got that right. So usually when you see this chart, you'll see Fe as the highest point on the chart because they've recalibrated the binding energy to be positive numbers. But this is the right way to look at it, right? Iron is actually at the bottom of a well. And so when you are fusing lighter elements into heavy elements, this is where all the energy from fusion comes from. As the nucleons fall and fall to lower and lower energy states, just like in the previous chart when the rock falls to lower and lower gravitational states, the nucleons are becoming more and more tightly bound until you have an inflection point at element number 26. And then after that, fusion actually doesn't give you any more energy, right? These heavier elements release energy by fission, right? They break into smaller and smaller elements until they go down the hill to element number 26. And so by visualizing these, the binding energy as negative, you unify it with the gravitational one, right? And you see that what's happening with fission and fusion is the energy releasing reactions are those that bring you towards the bottom of the well, that are making you lose nuclear potential energy and therefore gain kinetic energy. But the entire time, right, these are all stable nuclei, more or less, and so then there is an attractive force, and that's the strong nuclear force that's holding them together, right? And so they are most tightly bound in the iron atom, right? And they are not as tightly bound in uranium-238 or helium, right? These are higher up. The nucleons are still bound. That's why they're negative strong nuclear energy, but they are less negative, right? They're weaker binding energies for these really low mass and really high mass nucleons. Okay, and then the last example I want to give you is the one that you should know from chemistry class, right? Which is the biology folks will talk about how ATP is shuffling energy around, And this is the one where it's the most tempting. I mean, I think I see this in the majority of books, actually, that oversimplify this. And they talk about, the energy between, this is a adenosine triphosphate. So it's that third phosphate, the bond between that third phosphate and the rest of the molecule is the one that gets broken and reformed when you go from ADP to ATP, right? And so here's the typical chart that you get, and people are imagining that zero is way down here. And here's the energy that's released as you go from, the bond in the adenosine triphosphate to the products. And, this isn't entirely wrong, except that these are all negative numbers, right? And so if you ask a student, where's the weaker bond? The adenosine triphosphate, that third phosphate way out there that's in the reactant, that is a super weak bond, right? And after it breaks off of the ATP molecule and then snaps in with a water molecule or some other molecule that is nearby in the cell, it forms a much stronger bond, right? And so the product down here is the stronger bond. So if you're thinking about this as the 0 point of energy, that's very confusing. You're like, oh, this one's way up here, so this should be the strong bond, and this one's way down here, and so this one should be the weak bond. But it's actually the opposite, right? The third phosphate is hardly held at all. That's a super weak bond. And if you think about the 0 point being above the title here and the depth of the well being the strength of the bond, you'll see, that the reactant is a weak bond. And then the product is way down here in a deeper well, which, means more binding energy, which means it's a stronger bond, right? And so that's the right way to think about it. It's much more complicated, but it is the correct way to think about it. So this idea, that bond is carrying around a lot of energy is related to the idea of like, oh, there's lots of, positive energy in these bonds that get released as they get broken and sent down here. Or, the rock has a lot of energy stored in the bond that gets broken when it falls. But in all of these cases, it's actually not... nothing is being freed, right? You're going from weaker bonds to stronger bonds, and that's where all of the energy production in your life is coming from, chemically, gravitationally, and nuclear. I've linked another, so I won't go on about it from right now, but this idea of E equals mc squared starts coming up usually when you start talking about nuclear energy and people start realizing that the mass of the nucleons is actually affected by that bonding energy. And once again, you need the negative sign to make it work out, right? So why is it that the mass per proton is different in the different nuclei? And the answer is yes, it is because of the binding energy, but the answer is that the more binding energy there is, the more tightly bound it is, the more negative it is, and yeah, there's a decrease in mass, right? So the mass is actually coming from the energy within, which is what the other presentation that I've linked for you is about. And the other thing about this that I want to point out is that's not unique to nuclear reactions, right? That's true in all of these cases, right? Anytime you have a decrease in energy, the mass of the system is going down. It's just the scale of it, because the c is the speed of light, which is a big number, and when you square that, right, then it's a ginormous number, right? So the amount of mass by which the mass goes up and down is sort of almost inconsequential related to the amount of energy that goes up and down. So in everyday life, we just pretend like the mass is not changing. But there is no law of conservation of mass, right? That's just a lie. You're told it's a convenient approximation. The mass is changing all the time. A hot coffee cup, when it gets cooler, it weighs less when it's colder, right? Now, where does it weighs less in like the 8th decimal place, though? So, okay, well, I just wanted to talk about this idea about bonds and negativity and weak bonds to strong bonds. If this was confusing or not interesting or over your head or whatever, don't worry about it. But I felt like it was something I wanted you to see before you graduated. Okay, thanks for listening.